So welcome to video problem 23, which is entitled Displacement Current and Capacitor Problem. In this problem we are going to show that Ampere's law, as we know it from magnetostatics, will lead to a paradox for a capacitor which is connected to a time-varying voltage source, and also that this paradox is elegantly resolved through the so-called displacement current introduced by Maxwell to correct and generalize Ampere's law for time-varying fields. So this is our configuration of a capacitor with this capacitance Cp, which is connected to a time-varying voltage source. The voltage is given by the expression here, where V0 is the amplitude of the voltage, omega is the angular frequency, and T is the time. The voltage source will give rise to a current in the wires of the circuit, and this is more specifically known as conduction current. By using the capacitor equation given by the expression here, we can easily determine the expression or the value of this conduction current. As it flows through the circuit, it will give rise to a circulating magnetic field around the current, and we have here illustrated a few field lines for the magnetic field intensity. And now we would like to determine the magnitude of this magnetic field intensity around the wire. At least if our observation point, which is shown here, is close to the wire and well away from the capacitor gap, we essentially have a cylindrical symmetry, and the situation is equivalent to that of an infinitely long wire. From magnetostatics, we know that in those symmetrical cases we can use Ampere's circuital law, which is stated down here, and this is the one that we have introduced back in magnetostatics. It essentially says that the circulation of the magnetic field intensity along some closed path C is related to the total current which is flowing through the surface that has this C as its boundary. Now in this case, the simplest surface to consider is this planar surface S1, and whatever current flows through the surface here is related to the circulation of the magnetic field along this path C, which is bounding this surface S1. And obviously the total current flowing through the surface S1 is equal to our conduction current, which is flowing through the wires. On the account of this symmetry, it is fairly straightforward to determine the magnetic field intensity at this particular point. The left-hand side of Ampere's circuital law is given by the expression here. In the situation illustrated, the H field will only have a phi component, and this is the typical dl element on that integration path. And as you can see, the angle phi goes from 0 to 2 pi in order to close the loop. The right-hand side is equal to the current flowing through the surface S1, and this is of course, as stated previously, equal to the conduction current. And this is straightforward to evaluate. The left-hand side will give 2 pi times the magnitude of the field times the distance to the observation point, and from that you can easily isolate the final value of the magnetic field intensity, or more precisely, the magnitude of this magnetic field intensity at that particular point. And this is something that we have determined by using Ampere's circuital law as introduced in magnetostatics. So just to remind you one more time, what it says is that the circulation of the magnetic field intensity along a closed path C is equal to the current flowing through the surface bounded by this path, and this law is obtained by using Stokes' theorem on the fundamental postulate on the differential form for our magnetic field intensity. Now we are mentioning here the current passing through the surface, and you can ask yourself a question: what if I take some other surface that will have this C as the boundary? In particular, if I, for instance, consider this balloon-shaped surface S2, which goes like illustrated on the figure here, and in particular it passes through the region of our capacitor over there. This surface also has C as the boundary, but as you can see, there is no conduction current flowing through the surface, as there is no conduction current flowing through the capacitor. If we are relying on Ampere's law over here, we obviously point out an inconsistency, because in this particular case the circulation integral of our magnetic field intensity will be equal to 0, and eventually the magnetic field itself will be equal to 0, since no current is passing through this surface S2. So we see that Ampere's circuital law, as we know it from magnetostatics, will lead to an inconsistency in this particular case of this surface S2. Of course, we didn't have any reasons to believe that Ampere's law will be valid beyond the region of magnetostatics, and on the following slide we will show how a generalized version of this one, known as Ampere-Maxwell law, will actually resolve this inconsistency through the so-called displacement current that will flow through this region of the capacitor. So this is the configuration now that we are considering in order to determine the magnetic field through the displacement current. So in this case, the relevant surface that we are considering is this surface S2, and whatever current flows through this surface will then be related to the circulation of the magnetic field intensity along this path C, which is bounding this surface S2 in this particular case. So what is this displacement current about, and why does it occur in this particular case? Well, we have a time-varying voltage, and of course this time-varying voltage will give rise to a time-varying current in the wires of our circuit, and this current will of course create time-varying charges on the plates of our capacitor. And when we have time-varying charges on the plates of the capacitor, then also the field in the capacitor, the electric field intensity, and thus also the electric flux density, will be time-varying. And in those cases we have this generalized form of Ampere's law, which is more precisely called Ampere-Maxwell's law, where the circulation of the magnetic field intensity is not only related to this free current, but also this term over here, which is known as displacement current, and this was the term introduced by Maxwell in order to correct Ampere's law for time-varying fields. Now we have a time-varying field inside of the capacitor, and obviously this term will then contribute in this particular case to this circulation integral, whereas the conduction current density flowing through the capacitor will be equal to 0. So in order to finalize our calculations, let's assume that we are dealing with a parallel plate capacitor. The plates have a surface area A, and the separation distance is much smaller than the side length of these plates. We also assume a simple material in between the plates, which is then characterized with this permittivity epsilon. Under this assumption of closely spaced plates, we can depict a few of the field lines of the electric field intensity, and thus also the electric flux density, and these are shown on the figure here, implying a homogeneous field in our capacitor, and also zero fields outside. These are the assumptions that we are making in this particular case. Now, since the material of the capacitor is simple, the flux density is just the permittivity times the electric field, and due to the homogeneous nature of our field here, the electric field intensity is simply voltage divided with the separation distance between the plates. Now we know the voltage, we can plug it over here, and then we can calculate this time derivative of the electric flux density very easily with this final result. Now this is known as displacement current density, and we will have to plug it inside of this expression here in order to calculate this displacement current. And this is easily done. So in this calculation, the left hand side is of course 2 pi r times h. This is coming from the circulation of the magnetic field intensity along this path. This is equal to this current, and this current is of course equal to 0 when we consider surface S2, because there is no conduction current flowing through the capacitor. But then we have this other term which then takes over. D and the S element, which is the differential surface element of our surface inside here, will be in the same direction. So the dot product of the corresponding unit vectors will give unity, and obviously this integration here will simply amount to multiplying with the surface area of the plates, which is the area through which we are taking the flux of this partial derivative of the D field, or the flux of the displacement current. So we have the displacement current density times this area of our capacitor plates. Now we have epsilon divided with the separation distance times the area of the capacitor plates, and for a parallel plate capacitors this is giving you the capacitance in that particular question, so you can plug it inside here and finally derive the very same result for the magnetic field intensity, now on the account of the displacement current density, as we have done on the previous slide on the account of the conduction current flowing through these wires. So we can see how Maxwell, Ampere-Maxwell's law, or more particularly this displacement current term, is actually resolving the inconsistency in Ampere's law as discussed on the previous slide. So we see that the circulation of the magnetic field intensity, well, it is actually related to the total current flowing through the surface that has this path as the boundary. If we take this surface here, then it is the conduction current density, and in those cases here the displacement current density is 0. However, if we take this balloon shaped surface, well, the first term will be equal to 0, and then the second term will take over because of this displacement current density and because of the time variation of the electric field inside of the capacitor. So we are now arriving at the end of this tutorial. You can see Ampere's Maxwell's law, which is the one to use in case of time varying fields. And as usual, we have a task for you. You can see the configuration at hand on the figure to the right. We have a parallel plate capacitor which is actually charged with some charges plus Q and minus Q as shown over here, and this capacitor is being discharged through this resistance over here. The conduction current will be given by the expression here, and it will flow in this particular direction. It will pass through this surface S1. Since the charge will change with time, the field inside the capacitor will also do so, and will thus lead to a displacement current. What is the direction of the displacement current in the capacitor? Is it same or opposite to the field? Moreover, show that the displacement current flowing through the surface S2 that you can see over here equals the conduction current. Thank you very much for your kind attention.